So in addition to being aldoses, ketoses, and the number of carbons being part of the name, they can also form ring structures, right? And that's usually the bane of a lot of students' existence is when these things cyclize. So, and when they cyclize, if they form a 6-membered ring, and oxygen is always one of those members, it's a pyranose. If it forms a 5-membered ring, it's a furanose. And again, oxygen is always one of the 5 members. The other 4 are carbons, or the other 5 are carbons. But one oxygen is in the ring every time when it cyclizes. So, and the idea is this, and we're going to look specifically at D-glucose here. So when this thing cyclizes for D-glucose, most commonly it is the OH on carbon number 5 that comes and attacks the aldehyde carbonyl. Notice OChem taught you that when an alcohol attacks a carbonyl, we call that thing either an acetal or a ketal. It was very late in OChem 2 that you learned this. So in this case, if it attacks an aldehyde, we call it, so on our way to an acetal. So, and it turns out if only one alcohol attacks, it's a hemiacetal. If a second equivalent comes and attacks, it would be called an acetal. So in this case, with only one alcohol coming to attack, this is just going to be a hemiacetal that we're going to form here. So, and what that looks like in the cyclized form, we draw it a couple of different ways. So first off, when this happens, this oxygen, in some way, shape, or form, it's usually mediated through the solvent, but this hydrogen right here is going to end up on this oxygen right here. So this oxygen up here is going to end up being an alcohol. This guy's not going to be an alcohol anymore. He's going to be he'll look like an ether, but he'll be part of what we call the hemiacetal. Technically, that alcohol is the other part of it. So if we look at this, we can draw this in a couple of different ways. I'm going to get rid of our L-glucose, by the way. He's just in the way now. So if you notice, look at where your new alcohol is. And technically, this is really not an alcohol. These are all alcohols, but he's not an alcohol. When this carbon is partly an ether on one side and partly an alcohol on the other side, he's actually not an alcohol or an ether. His new name is, again, hemiacetal. This thing's a hemiacetal. And if you look, so look back at your aldehyde carbon. What's his hybridization right here? sp2. What's the geometry of an sp2 hybridized atom? Trigonal planar. This thing is flat right here, flat geometry. When this alcohol comes to attack, it can come from the front face, or it can come in from behind on the back face. So and depending on which face it attacks from, that's going to affect the stereochemistry around this carbon right here. This carbon used to be sp2. He's now sp3. And because he's sp3, and now he has 4 different groups, what is he? He's a chiral center. He used to not be a chiral center here. He's just sp2. You can't be chiral with an sp2. But now, in the cyclized form, he's now a new chiral center. That new chiral center you form when you cyclize is called the anomeric carbon. Anomeric carbon. And again, because you can attack it both from the front face, the carbonyl from the front face, or the back face, you can form both the R and the S versions of this, which we're not going to call R and S. We'll refer to them as alpha and beta, as we'll see in a little bit. But what used to be the carbonyl carbon, that's your anomeric carbon. Notice on an aldehyde sugar, that's carbon number 1, because the aldehyde's always at the end of the chain. On a ketone sugar, it's not going to be carbon number 1. The anomeric carbon will be some other carbon besides carbon number 1. Like in fructose, it's carbon number 2, as we'll see in a little bit. But if we want you to draw the cyclized form of this is not usually what we have you draw, right? So we have you draw oftentimes what's called the Haworth projection. And if you look at the way this is numbered now, 1, 2, 3, 4, 5. Way this works, whatever comes, so there's your anomeric carbon, right? First off, carbon number 1. And you can form both versions of that chiral center, and one's called alpha, one's called beta. We'll get back to that in a sec. So, but carbon number 5, first off. So in this case, carbon number 5 is the one that had the alcohol that came and attacked. The carbon that's on the other side of the oxygen, away from the anomeric carbon, may not be carbon 5, but whatever carbon that is, whatever its group, which in this case is carbon number 6, wherever that comes off tells you if it's D or L. When that group, which in this case is CH2OH, goes up, that tells you it's a D sugar. And because 95% of the time students never even see an L sugar look like this, they don't realize that they've never seen an L sugar. The L sugar would have had this CH2OH point down instead. But it's a D sugar. So also, because 95% of students have only ever seen a D sugar, when they memorize what alpha and beta mean, what they don't realize, they've only memorized what it means for D sugars. It would actually be the opposite for L sugars, as we'll see in a little bit. Cool. The other side of the coin is things that are on the right here, the ones that are still alcohols here. Where do things on the right point? Down. Oh, that's just downright dirty, right? So down and right go together. So in this case, the OH on carbon 2 points down. And the H, which I won't draw in, points up. The OH on carbon 3, though, is on the left, so it points up. The OH on carbon 4 points, it's on the right, so it points down again. Cool. Why don't I have to worry about the OH on carbon 5? It's not an OH anymore. It's this O right here. Cool. Now we got to worry about the new alcohol on carbon number 1. So, and technically the way this works, that OH could point up or down. And so I'm going to give you the rule for just D sugars in a second, because that's what you're most likely going to see. So for D sugars, if the OH points down, what did you learn that actually meant? What's the designation we give for that? Alpha. Notice it's convenient that the OH pointing down is alpha, like you're swimming down with the fishies. So alpha means down. So however, bless you. If, however, on that anomeric carbon, that OH points up, that's beta. So it turns out that alpha has the OH pointing down and beta has the OH pointing up only applies to D sugars. So here's the real rule. Here's the real rule. If whatever's coming off of carbon number 5 here, it doesn't have to be carbon 5, but whatever's on the other side of that oxygen, whatever group's coming off there, whatever substituent, if it and your OH on the anomeric carbon point in opposite directions, that's alpha. If it and the OH on your anomeric carbon point in the same direction, that's beta. That's the overall rule. Because notice, what did we say would be different about a D sugar? Where's this point on a D sugar? It points down. And so if the OH also pointed down, that would be considered the same direction as it. And on an L sugar, that would have been alpha. I'm sorry, that would have been beta, not alpha. It would have been the exact opposite. So this idea that alpha means down and beta means up only applies to D sugars if this substituent itself is pointing up. Again, 95% chance that you're probably only going to ever see a D sugar. I just want to give you the overall rule just in case you get that other 5% chance. Just FYI. Again, you guys being 361 as well, a little even less likely that you're ever going to see it. I just want you to know the real ultimate rule just in case. Any questions here? Okay. Good. One of the members is always oxygen. So in this case, how many total atoms are in the ring, including the oxygen? 6. So this would be considered a pyranose with glucose. We'll see the most common cyclized form of fructose in a little bit is actually a furanose, a 5-membered ring. But yes, oxygen does count as one of those members. Hama.
So when we learned that the heavy acetal has ROH and HO group, OR group?
Yeah, so if you notice, you look for the carbon. If you're trying to find the anomeric carbon in a sugar, find the carbon that's bonded to 2 oxygens. Notice, is this carbon bonded to 2 oxygens? No. It's going to be on one side of that oxygen. but it's the carbon that's bonded to two oxygens. One of them's an OR. R can be any carbon chain, and this is just a big cyclic carbon chain, right? And the other one is an OH. That's the hemi.
And then is the other H R group?
Now, if I change this to another OR group, that would make it an acetal in this case. But with one being an OR and the other being an OH, it's just a hemi-acetal. And we'll show an acetal in just a sec as well. So in this case, your alpha and your beta, they can actually convert back and forth. So, and how do they convert back and forth? Well, the ring just opens up. Technically, this guy's like, I'm tired of being alpha. I'm going to go back to being open chain. And then I'm going to turn into beta instead. And so technically, there's an equilibrium here between these two, but this is the intermediate between them. This thing opens up and then turns into beta instead. This process of the interconversion between alpha and beta cyclic forms via the open chain form, we call that mutarotation. And as long as your sugar is in the hemiacetal, like in this case, or hemiketal form, mutarotation is possible. We'll find out, though, that if you put it in an acetal or ketal form, you can't mutarotate. It's frozen in whichever form it's in. We'll see that in a sec. So if we compare glucose to fructose for a minute, so first of all, fructose is still a 6-carbon sugar. And what do you call a 6-carbon sugar? Hexose. So, but in fructose's case, it's a ketose. It's a ketone sugar, not an aldehyde. And it looks remarkably like glucose. It's actually an isomer of glucose. If you notice, the stereochemistry around carbons 3, 4, and 5 is exactly the same in fructose as it was in glucose here. Specifically, is this D or L fructose? D. What told you that? Carbon 5, OH on the right. Sweet. So this is D fructose. Cool, and he's a ketose instead. And so now in this case, if we cyclize this guy, again, it's going to be alcohol on carbon 5 coming around. Cyclize, but in this case, instead of forming a 6-membered ring, notice he's just a little bit closer than the end of the chain was, like he was on glucose. And so I'm going to form a 1, 2, 3, 4, 5-membered ring instead during the process. And so the cyclized form of fructose, actually I want to leave that up there, darn it. The way this is going to work is we got carbon 2, 3, 4, 5 in the ring. And notice we joined, so in this case, my bad, carbon 5's OH attached to carbon 2. And so carbon's 5O is bonded to carbon 2. So that's the first part. And because this is a D sugar, it's this guy, carbon 2, is the anomeric. Let's highlight him first for a sec. The other side of the oxygen, whatever attached to that carbon, that's what determines if it's D or L. In this case, I want to make it a D sugar. So on carbon 5, your CH2OH group should point up, just like it did on the cyclic forms of D-glucose. Cool. The OH on carbon 4, what does it point? Down. It's on the right. It's downright dirty. So where does the OH on carbon 3 point? Up. It's on the left. So where's the OH on carbon 2 point? It depends. So notice carbon 2 didn't have an OH. He was an sp2 hybridized carbonyl. But when we attack him, he becomes a brand new alcohol now. And so now, if the OH points down, relative to this guy, that would be considered alpha. And if the OH points up, he's going to be beta. Well, I'm going to make him beta. Put the OH up here. But what else is carbon 2 attached to? Carbon 1. And so carbon number 1 is this CH2OH right here. And so I got to draw him in as well. And again, carbon 2 in this case, the one that used to be the carbonyl, he's what we call our anomeric carbon in this case. And again, he's anomeric because you can form 2 different chiral forms of him, the R and the S, the alpha and the beta, if you will. In this case, if you just were given this structure and you were asked if it's alpha or beta, how would you find your anomeric carbon? Well, he's always next to the oxygen in the ring, but there's 2 carbons next to him in the ring. How do I know which one? The one that's bonded to 2 oxygens. One of them's an OR, one of them's an OH, that's a hemi. And in this case, though, is that the end carbon in the carbon chain? No, if you number the carbon chain through, 1, 2, 3, 4, 5, 6, he's not the end carbon. And so in this case, he's a hemiketal, not a hemiacetal. He came from a ketone, not from an aldehyde. Cool? So in this case, how big is the ring total? Atoms in the ring? 5, including the oxygen. So what is he? He's a furanose. Cool. So now you've seen both pyranose and furanose as well.